Okay, everybody. So let's take a look today, okay? We're going to start calculus here, and the main thing I want you to get out of this, hey ladies, I'm starting now, okay? The main thing I want you to get out of today is this whole idea of something called the tangent problem. Now, before we actually talk about the actual problem, let's just review some terms, okay? Anyone remember what a secant line is if I give you a graph? So let me just draw a graph. You draw this in your notes too. Whee! Okay, there's your graph. If I asked you to draw a secant line, what would you do here? Draw a line that does what? It doesn't have to be perpendicular, but it goes through, yes, Victor? Not divide by 2, but it goes through, I guess I'll say this, it goes through at least 2 points, like that, okay? So the definition of a secant line, of course, is a line that I say passes through 2 points, okay? And we've done stuff like that before. If I have 2 points, you should be able to find the equation of the line because you can find the slope and all that kind of stuff. Good old grade 10. Okay. Now, what's the difference between something called a secant and a tangent then? Anyone remember what a tangent means? Touches at one point, right. So if I were to draw a tangent line, I'd draw something like this, okay? So you draw it in. Tangent line, and of course that's a line, and I'll say that touches the graph at only 1 point. Okay. Question from Katie. Go. Yep. It could be more. Yeah, it could be more, but at least 2 points. So pass through. How about this? I'll go at least. Thanks, Katie. Okay. All right. So those 2 terms you should have done before. We've got some more things I want to quickly review before I actually start doing this stuff. So what's the format for the equation of the line? If I asked you for the equation of a line, good old grade 10. Anyone remember that? Yeah, y equals to mx plus b. Good. That's one form. This is what they call the slope-intercept form. There are other forms which I don't know if you like or not, but I'll just show you another one that many university people use. It's this one, y minus y1 equals to m bracket x minus x1. Remember this one? Yeah? This is called the slope, and because you have y1 and x1, this is called the slope point form. So we did all this stuff in grade 10. You review your notes from grade 10 if you still have them, okay? And if not, then go find some grade 10 friends and borrow their notes, okay? And then one other thing I'd like to review before we even start our first adventure into calculus is what's the formula to calculate the slope between 2 points? y1 minus y2. I use y2 minus y1, but okay. All over x2 minus x1. And if you remember the song, anyone remember the song? Slope equals y sub 2 minus y sub 1, yeah, all over x sub 2 minus x sub 1. Yeah, row your boat. Good stuff, good stuff. Okay, ladies and gentlemen, all that stuff that we learned before, we're going to use again today to introduce to you the idea of this tangent problem in calculus, okay? So let's take a look at example number 1 together. I'm going to ask you to please find the slope of the tangent line to this graph, y equals negative x squared, at a particular point, 1 comma negative 1. Okay? How many of you have a ruler, by the way, or a straight edge? If you do, it'd be nice if you bring one out. Okay? I'm going to ask you to see if you can visually draw the tangent line at 1 comma negative 1. Okay? So on your notes, okay, see if you can visually draw the tangent line. And I'll do it in red, okay? And this is a tangent that is at this particular point, so 1 comma negative 1. And I'd like you to draw the best you can the tangent line here, okay? Maybe that doesn't look that good, but do what you can. Right? Now, ladies and gentlemen, your job is to find the equation of that line. Okay? Now, of course, because you've drawn it in, you can kind of find points and all that. But let's say we actually didn't know where that line was. Bless you, Vincent. The question today is how are we going to actually find this slope of the tangent line? We're going to use the formula. Good. So what's the formula for slope? Let's write it down again. Slope equals y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. Okay, my problem here is what's my x sub 1, y sub 1? What's my x sub 2, y sub 2? Do we have a point, by the way? Yeah, which point? 1, negative 1. Good. We have at least one point. Where's our other point if we're going to make this slope? 0 and 1? Over here? Over here? Over here? Where should our other point be? 2 and what? Like over here? Well, I want to not, let's look at the line right now. Pretend we actually didn't have the line right now, okay? So if I didn't have that line, where would my other coordinate be so I can find the slope? Origin, maybe. Actually, I don't know where, okay? The goal here is I don't know where, and that's my problem. So I can't actually go ahead and find the slope of the tangent right away. But what you can do is maybe find the slope of a, not a tangent, but perhaps a secant line. Don't draw this in, just watch. Maybe a line like this, okay? Or maybe a line like this. Or maybe a line like this. I don't know, all these different lines. Some of these aren't very good approximations, right? But what I'm saying to you is we need 2 points. We've got one, but we need another one. So I'm just going to call this other point over here. And because I don't know what it is and I want to generalize it, I'm going to use variables. Which variables do you think? How about x comma y? Good. Okay. So this x comma y represents any point on this parabola. Okay. And I'm going to pretend that we have a fictitious point here in blue, and I'm going to ask you to draw in the, and what type of line am I drawing here? Secant line. Good. Okay. Yeah. Don't erase your tangent, just leave it there, but just draw a secant one as well. Okay. Now, dear friends, I'm getting scared because, look, I've got an x. I've also got a y. That's not so good for me. Don't like x and y's. I want just x and something else with x. So, can someone suggest to me what I can replace y with that's in terms of x? What is y equal to? What is this function equal to? Yeah, it says negative x squared. So I'm going to ask you to rewrite this coordinate like this. X comma negative x squared. Okay. That's going to help me out because now I only have one variable to deal with, not two. I hate two variables. Okay. All right. Here's what I'd like you to do next. Can you now take these two coordinates, okay? Call one of them x1, y1. Call this other one x2, y2. And can you now plug it into the slope formula to find an expression to find the slope of this blue line, okay? So I'm going to ask you to use our slope formula. What's y2 in this case? Can someone help me out? Negative what? X squared, good. So we're going to go negative x squared minus, now what's y1? Negative 1, good. All over x2, which is my x, and what's x1? Which is 1, good. And I'm going to ask you to please simplify this if you can. I think this becomes negative x squared plus 1 on the top, and then we have x minus 1 on the bottom. And what I'd like us to understand is that this is our formula for the slope, okay, of a secant line. Yes, Vincent. I don't want you to factor right now. You can, I know you can do that, but let's just not do that right now, okay? And I want you to box this for me, please, okay? This is important. Okay. Now, that is our slope equation. Yes, Anna?
Is this the formula for all secant lines or just one secant?
All secant lines, but this particular one is the formula for all secant lines of this graph using this point, 1, 1. right? Because these are x values. You can choose any x value. So what I'm saying to you, Anna, is if I chose x value of 2, then I plug it into this formula, I get the secant line looks like this. Okay? If I chose an x value of -1, I get the secant line that looks like this. So I'm drawing all the different secant lines, or I'm sorry, I'm not drawing. I'm calculating the slopes of all secant lines that go through this point and any other point along this parabola. Only this point right now, yeah. Okay? Now, here's the deal. Is the blue line a good approximation of what the slope should be? Of the tangent line, first of all? Maybe, but I thought we wanted something that looked like this, right, that we drew earlier. So the question for you now is, how do I get this blue line to look like this red line? Okay, and let's just take a look really quickly here. I'm going to bring up this applet. Whee, pretty. Can you see how we have this here? Here's my parabola, right? Y equals -x squared. Okay, and here's my tangent line. Now, I'm going to change this value, okay? Let's pretend that this value here, the secant value, is 2. So here's what I got, okay? So you see what we've got here? Let me get rid of that. Get rid of that. Okay, you see this point 2? That green line is exactly like what I'm drawing in my notes in here, which is my blue line, okay? I'm going to ask you this, ladies and gentlemen. If this was at 2, okay? So let's take a look at this now. Let me draw one more line for you. Just watch first, and then I'll hopefully get you to write this down. Let's say I had a line here. Okay, I'm going to draw this line in green. Okay. Let me ask you now to calculate. Okay, I'm going to ask you to find the slope of that green line. Okay, and the green line is when the x value is equal to 2. Okay, now how would you do this with this formula? Just watch me first. Okay, give you a chance to write this down in a second. What would you do? Plug in 2. Good, so let's plug in 2. Okay, so watch first. Don't write this down. Just watch. -2 squared plus 1, 2 minus 1. What do we get here? Help me calculate. 2 squared is? 4. So -4 plus 1 is? -3. So -3, 2 minus 1 is? 1. So this whole thing here has a slope of -3. And this is what I believe this graph also says. I don't know if you can see it over here. Secant slope, you see that? -3. Once again, is this a good estimate? No. So what should I do to make it a better estimate for the tangent? What should I do at this point? Move it up. Okay, so watch me move it up. Move it up to where? Here, 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 here. Okay, so as close as possible to 1. Now let's say I left it at like 1.5, like right about here. Okay, let's make it 1.5. 1.5. Let's go ahead, 1.5. And if I enter and calculate it, look what it does. It actually calculates what the secant slope is. It's actually -2.5. Now, let me just show you one more time in our notes, and then I'll give you a chance to write this stuff down, okay? Where are my notes? Here they are. Okay, so let's do another one. This one was too far. Let's go closer. Let's go closer. And you told me to choose, what, x equals to 1.5? So once again, I'm going to now take this value of 1.5 and stick it into the slope formula. And let's go ahead and calculate this. Oh no. What's 1.5 squared? 2.25. -2.25 plus 1, -1.25, is it? And then divide by 0.5, so that's times by 2. Oh yeah. Okay? Now, ladies and gentlemen, I'm going to ask you to write this down now. Okay? Write down these two. And then I'm going to ask you, this is still not good enough, so I want you to choose another one. Go even closer. Okay? And I want you to decide what value to choose for x, and then go ahead and calculate as well. Okay? So now is your time to, okay, so once again, we're trying to find a point closer and closer to 1. We can't choose 1 once again because when I plug in 1, you get 1 minus 1, which is 0, and you're dividing by 0, bad news. So choose something as close as possible. And what do we have here as the number? Can someone shout it out? -2 point something. I want the something. 0, 0. 0. Okay, fine. 2 with a question mark. Okay. Now, ladies and gentlemen, once again, we're not asking for an approximation. We want the actual number. So, what I like us to do next is this. Okay? Look at what we're saying underneath here. As x approaches to 1. You see I'm using this word approaches. Okay? You see I started at 2, then I went to 1.5, then I went to 1.001. You see I'm getting closer and closer, approaches to 1. The slope of this secant line becomes the slope of what type of line? The tangent. Exactly. Okay? And because the slope of the secant line becomes the tangent line, in this example, can you tell me what the slope of the tangent line is going to be then? Probably -2. Good. Okay? Now, ladies and gentlemen, here's your initial taste of what calculus is going to be. Okay? You're not going to be doing this method forever, but this is the basis of what's happening. And as we go through our studies, you'll learn a very quick way to calculate the slope, not doing all this stuff, but the basis and the rationale behind it is what I'm doing here. Okay? Now, let's continue. Example number 2. Okay? Tony, can I get you to move, please? Right here. Okay? Now, what I'd like us to do next is example number 2. Let's see if you can now extend this and find the equation of the tangent line at 1, -1. Okay? So we found the slope. Okay, so the slope from above, I'll say the slope of the tangent from above, okay, is -2. And you also know that the equation of a line from way, way above is what form? Y equals to? Y equals to? Mx plus b. Thank you, Vincent. And then you know that it goes through this point, which is called 1, -1. So can you actually go ahead and find the equation of the line? Please say yes. No. Maybe. What's the first step? What's m? -2. Yep. Okay. And then if you want to solve for b, what do I do in here now? Plug in the point, right? So let's plug in -1, -2 times 1 plus b. Okay. 2 minus 1 is 1. 1 equals to b. Whoa, look at that, dear friends. Y equals to -2x plus 1. Okay. Now, once you've done that, before you turn the page, I'd like you to go back to your picture, your graph, and look at that tangent line we initially drew. Can you double check that the equation of that tangent line is exactly the same as this? Okay. Does it look the same? That red line here? Look at the slope. 1, 2, 1 to the right. That's okay. What's the y-intercept? It looks like it goes through 1. Oh yeah, it works. Okay. So this is the equation, and please write this down. The equation of the tangent line. Okay? All right. Ladies and gentlemen, can I get you to start the next one on the next page, the application, or the exercise, sorry? I'm going to get you started on this, but I'm not going to finish it because I'm running out of time. I do want to show you example number 3 as well, and then after that, you should be able to do the rest on your own. Okay? So with exercise on page number 2, I said let's use examples 1 and 2 as a guide. So let me set up the equation, and then from there you can finish off the rest. Okay? Let me just quickly draw out what this square root function looks like. Anyone remember what that looks like? Yeah, sideways parabola. And you've got the point here. We'll call it 4, 2. See all this lovely review from chapter 5 now in Math 11? Chapter 5 is this radical stuff. We did radicals? Some of us did if we were awake. Okay. Okay, now remember, our goal is to find the equation of the tangent line. But before we do that, let's find the slope. And I'd like you to find the slope between 2 points. Okay? What do I call that next point again on this parabola? Or not parabola, this is a square root function? X and y, but let's not use y. Let's use something else. X and square root x. Awesome. Okay? So let's go ahead and calculate the slope, please. Oops, what happened there? Weird. My point got shifted. I'll close the door. Okay. Okay, so go ahead and calculate the slope, please. Use your y2, y1, x2, x1, all that kind of stuff. Okay, so let's use root x. So slope here equals to root x minus 2 all over x minus 4. Okay? All right. Now, here's what I'd like you to do now. Okay? I want you to try to use this slope formula. So use slope formula to find the slope of the tangent line at x equal to 4. Okay? So this is the part where you plug in numbers. So the question is, what number do you want to plug in? Any suggestions of numbers? 2? But I don't think that's going to be a very good approximation if it's 4. Yes, Anna? Yeah. Sure, 4.0001. Okay, it could be 4.00001. It also could be 3.99, right? And all that kind of stuff. So why don't you go ahead right now and choose a value, plug it in, and let's see what you get. Okay? So choose something close to x equals to 4. So somebody back there said 4.0001. Okay. Calculate, please. Katie, use your sparkling personality and calculate. Oopsies, minus 4. See, making silly mistakes just like regular Math 11 students. Yeah. Part of my teaching persona. Okay. So that should be minus 4. And go ahead and calculate this. Can someone tell me the answer when you've got it? I think it's going to be a decimal. 0.25? Yes, 0.25. So this is pretty close to 0.25. And that's approximately just 1/4, right? Okay. Okay, ladies and gentlemen, you keep going now. Can you please find the equation of the tangent line? Because you now know all the information you need to find the equation. You've got the slope. You've got the point. Go ahead and try this on your own. Leave you. Okay? So, for those of you who are doing physics, yay, you'll actually see that physics and calculus go hand in hand. Okay? One of the reasons is, you know that guy that did a whole bunch of physics stuff? What was his name? Newton, right? Newton, the guy with the apple. Well, guess what? You know what? He's the same guy that did calculus, if you think about it. So, yeah. Okay? So, it's kind of interesting. There's a story about these two competing mathematicians. Okay, one was Newton in England, and there's a guy named Leibniz in Germany, and they both started developing calculus at the same time. Seriously, but of course back then they didn't have Facebook, so they couldn't control each other. So what did they do? Well, they didn't know about each other. So Newton developed his, Leibniz developed his, and then all of a sudden, guess what? Okay. So here's an example that you've seen before in physics. Find the velocity, okay, the speed, right, of a free-falling coin, and I'll say 3 seconds after being dropped from the top of a skyscraper 200 meters above the ground. Okay? You've seen this before in physics. This is what I'm going to ask you to do. Okay? I want you to find the velocity at a certain time, at 3 seconds. Okay? So when I want a velocity at an instant in time, this is often called the instantaneous velocity. Okay, heard that term before in physics?
Yes.
Yes. Okay. Now, how is this different than something? Oh, by the way, before I do that, recall then for a free-falling object, the displacement or distance is given by this equation. S, which I call distance or displacement, is 4.9 t squared. Do you know where that 4.9 came from? Right, that's right. Half gt squared, right? Gravity's. Well, I just rounded to 4.9. Okay, I'm math. Doesn't matter. Now, before we actually do this question, let's go back to this idea of average velocity. How do we find average velocity in physics? Change in what? Okay, I'm going to use the word displacement, but yeah, change in distance, sure. In this case, the same thing. Over the change in, yes, I heard that, in time, right? Okay. Yeah, it is, same thing. Distance, displacement in this case is the same, because I'm not going back and forward, right? I'm just going one way. Now, in terms of your slope formula, and it's not y2 minus y1 now, I'll use d2 minus d1, t2 minus t1, right? That's the average. Okay, now, before I actually do this question, let me just quickly talk about the difference between average and instantaneous, okay? Think about this. Average is comparing your start to the end. So you're in a car, you're driving to Burnaby South, okay? Slowly, fast, 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 slow down, stop, okay? So if I asked you for the average velocity, you're taking the change in the distance, how far you traveled, divided by time. So maybe like you traveled 10 kilometers in, I don't know, 2 hours. So your velocity here is 10 divided by 2 is 5. How is that different than instantaneous? Here's the difference. Traveling, traveling, traveling. Here's the movie of you watching yourself travel, 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 right? But instantaneous means travel, 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 press, pause. Okay, so at a certain time, you're pausing. And at that moment in time, at that instant, how fast are you going? Okay? So think. Travel, 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 pause, right? While I'm pausing, at that moment in time, what is the velocity? That's what I mean by instantaneous. Okay? Instantaneous. It's like when you're watching this video and you press pause, like this. Anyways, let's see how we can calculate this now. I know, I just paused it. How do I calculate this now? Let's go ahead, please, and use our slope formula. Okay, now do we have a D1 and T1? Do we have an initial time? We do. Our initial time is what? No. I want it at what time here? 3, right? So in this case, let's call T1 equals to 3. What's our corresponding D1 going to be then? We're going to put it into this formula. Sorry I used S. Maybe I'll use D just to make it easier. So let's go 4.93 squared. Okay, what's 3 squared? 9. 9 times 4.9. What is it? 44 point what? Help, help, help. 44.1. Thank you. Okay. So there's our initial T1 and D1. So our first coordinate is 3 and then 44.1. And remember, the average velocity here is the change. So what do we do with all these other questions? We picked a different variable. So let's call the other one, I don't know, let's call the other time, let's say T2 is equal to, you guys like X, right? So I'll just use X. What's D2 going to be then, if I use X to represent that? That would be 4.9 X squared, right? Once again, plugging it into that formula. Okay. So with all this information, I'm going to ask you now to plug this into our formula for average velocity. Okay. So D2 is 4.9 X squared minus D1, which is 44.1. And I'm going to divide this by T2, which is our X value, minus T1, which is 3. So if you think about what we're doing right now, it's exactly the same as what I did before in example number 1. Okay, trying to find the slope or calculating the average velocity. Yes, Bronte. But my formula here says the displacement traveled after this many seconds, so I'm actually assuming it's starting at 200, but I'm using that as 0.
Oh, is that like stuff that you put 50 as well?
Yeah. Yeah. So just be careful here. After t seconds, so you really don't need this 200 anywhere. It doesn't factor into anything. So red herring, right? You know how the physics teachers do that? They put in some stuff and they just trying to give you a taste of what to come. Okay, ladies and gentlemen, this is the formula for average velocity. How do I calculate, I guess, the instantaneous velocity? Well, what number should I plug in for x here? Okay, so to calculate or to find the instantaneous velocity, remember what instantaneous means again? Instantaneous means at the actual moment in time of 3. So what I want you to do is to find the instantaneous velocity. What value should you choose for x? Choose x equal to what? 0. 0 is not close to 3. Yeah, choose something like 3.0001. Okay, so go ahead and do that for me, please. Go ahead and plug that into our formula, and I'm going to ask you to figure out what this so-called instantaneous velocity would be. Okay. Can somebody quickly do this for me? Yeah. The problem is you can't use 3, Vincent, is if you look at the average velocity formula in blue, if I plug in 3 into the denominator, you get 3 minus 3 is 0. So it's because we can't divide by 0, we can't use 3. You're right. The best answer would be to use 3, but we can't. Yet. We will be in a second. Stay tuned maybe for next day's lesson. Okay? Now, what do we have here as a number here? Is it 29 point something? 29.4? Good. Meters per second. Now, if I had more time, I'm going to ask you to do another one for me. I'd choose a number even smaller than that, 3.00000001. Okay, but I'm not going to do that right now because I don't have time. But what you should do is try as many points as close to 3 as possible to see what it looks like. I'm going to summarize this below. Okay, therefore, I'm going to say the instantaneous velocity. Okay, the instantaneous velocity at t equals to 3. Okay, now when I try different values closer and closer to 3, I'm calling this the limiting value. By the way, hint, 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 limiting, limit. Mean Girls? Okay, stay tuned for Mean Girls. Okay, so the instantaneous velocity at t equals 3 is the limiting value of the average velocity. Okay, over short periods of time. Okay, notice what I mean by short periods of time. 3 and 3.0001, that's a very short instant in time. Okay, so by doing these calculations, what is the instantaneous velocity? Okay, I'm going to ask you, what is the instantaneous velocity when the coin has dropped from the skyscraper after 3 seconds? Yeah, it's just 29.4 meters per second. That's pretty fast, okay? That could probably put a big dent in your head. Meters per second, not kilometers per hour. Meters per second. That's fast. Okay, ladies and gentlemen. This is an intro to calculus, all right? What I'd like you to do next is try example number 4 right now, okay? And then after you've done that, can you please work on the questions in the back, okay?